Good afternoon, students. Welcome to the live lecture of Real Analysis 1. In the last lecture, we have seen the second definition of integrability, also called as the Riemann definition of integrability. According to this definition, the function is said to be integrable on the closed interval AB if limit of this SPF, limit with respect to which either UP tends to 0 or n tends to infinity. If the limit exists, then we say that the limit value of this is nothing but the actual integration A to B. In terms of epsilon delta notation, we can write the same definition like this. Okay. Later we have seen the equivalence between the two definitions of integrability. To prove the equivalence, we have proved that definition 1 implies definition 2 and definition 2 implies definition 1. That is, both the definitions are implies and implied by one another. Therefore, we can say the definitions are equivalent to one another. Therefore, one can use any definition for solving the examples or writing the proof of the given theorems. But according to me, it is better to use the second definition of integrability if you are solving the examples. First example, under this we have solved integration of the function 7x plus 3 between the interval 1 to 2. Correct now? Same method we have used. The given interval we have partitioned into n equal parts. Delta xi is the length of every subinterval we have written, which is 1 by n. We have marked the points xi minus 1 and xi of the ith subinterval, and the arbitrary point ti we have selected to be xi. Xi means which point I have selected actually? End point, no? This end point we have selected. Correct now? Xi minus 1 to xi. Second endpoint of the ith subinterval we have selected, and accordingly we have written SPF. Then we have evaluated the value, and lastly we can take the limit as n tends to infinity. By taking the limit, we can see that the limit exists. It takes some finite value. Therefore, we said that the limit exists, and whatever is this limiting value is nothing but the actual integration. This is what I have told you. 3 more examples I have given you to solve as a homework. Have you tried to solve this? Solve Caleb ka?
Yes, ma'am.
Good. Any difficulty while solving the examples?
No.
Good. Actually, in that second example, I think integration x square example, you have to use summation n square formula. That's it. Okay. Now let us solve one more example. This example is somewhat of different type. Therefore, I am going to take the example. The first example here I am going to take is the integral value of mod x function. Therefore, it is asked us to compute the integration from minus 1 to 1 f of x dx, where f of x is defined as mod of x. I think all of you are familiar with modulus function. Right now? How the function mod f is defined? F of x is equals to mod x. If I consider the interval consists of both positive and negative values. Therefore, what one has to take care? One has to take care with both the values, right? No. The interval is from minus 1 to plus 1. In between somewhere we will have 0. From minus 1 to 0, the behavior of the function is different. That of from 0 to 1, the behavior is different. Correct, no? What is the behavior of the function if x is non-negative? That is from 0 onwards. What will be the value of mod x then?
X.
X. Good. And if I take this to be x less than 0?
Minus X.
Yes, it is minus x. So that x itself is negative, with one more negative, it becomes the positive value. So modulus function is an absolute function converting the value of any number to a non-negative value. So as the function behavior is different on the given subinterval, here the function behaves as minus x, here the function behaves as x. So for whatever the process we were using, dividing the given interval into n equal parts, okay, is not suitable here, because nature of the function is different on one half and the other half. So what we will do, for the sake of convenience, we will divide the first half of the interval, that is minus 1 to 0, into n equal parts. Similarly, we will divide it in divide 0 to 1 into n equal parts. And then we will separate this integration of minus 1 to 1 as separately from minus 1 to 0 and 0 to 1, and we will solve the example. Is it okay? What about the function, bounded or not? You have to check this first, na? Whether the function is bounded. Bounded or not? माहिती का नाही बाउंडेड आहे की नाही फंक्शन? काय माहिती मॅडम?
Yes.
बाउंडेड आहे ना. बाउंडेड म्हणजे बाउंडेड कसं चेक करायचं आपल्याला? कसं चेक करायचं बाउंडेड फंक्शन? फक्त कुठे इन्फिनिटी येते का एवढंच बघायचं ना. इन्फिनिटी येत असेल तर बाउंडेड नाही आहे. इन्फिनिटी नसेल तर बाउंडेड. Okay. What will be a graph of the function? Can you tell me the graph? Do you know the graph? Function model? Modx?
V type.
Yes, it is V type. Very good. It is a function modx. Okay. But here I can say the function bounded and continuous as well. Now let us go for making the partition. What the idea I have told you to make the partition? We are going to divide the interval minus 1 to 0 into n equal parts and 0 to 1 into n equal parts. Now you have to tell me what kind of interval will be. Minus 1 to 0, what is the length?
1.
Length of the interval? 1. Therefore, each subinterval is of length. If I divide into n equal
1 by n.
parts, 1 by n.
1 by n.
Can you tell me the points? How should I mark the points? Minus 1. Next point with length of the subinterval to be 1 by n.
Minus 1 plus 1 by n.
Very good. Next, minus 1 plus 2 by n. And continuing like this, this is minus 1 plus n by n is plus 1, therefore it is 0. Now, from this onwards, again we will try to divide into unequal parts. Length of the interval is 1, therefore each subinterval will carry a length of 1 by n. What should be this point, next point to 0?
1 by n.
1
Yes,
plus
it
1
is
by n.
1 by n, 2 by n, and so on. Somewhere here it is n by n, that is 1. Is it okay? Try to understand why we were making the different partition of this one interval. Because function behavior is different on the different parts of this interval. Okay? Therefore, shall I write the partition? Let the partition. Or before that, what I will write? Let us divide the interval minus 1 to 1 into n to n equal parts, right now? 2n equal parts, comma, length of each subinterval will be, yes, what will be the length of each subinterval? What is the total length of your interval? Minus 1 to 1. Minus 1 to 1. What is the total length of the interval? If you have a closed interval a to b, how you are finding the length?
P minus a.
A minus
b
b.
minus a, right now. Therefore, what will be a length here? 1 minus of minus 1, that is 2. And this 2 we were dividing into 2 unequal parts. What will be the length of every interval?
1 by n.
1 by n.
1 by n. Okay. Now let us write the partition. Let the partition be. Partition P we were writing as a collection of points. First point minus 1. Next minus 1 plus 1 by n. Minus 1 plus 2 by n. Correct now? Somewhere this is 0. Then 1 by n. 2 by n. So on up to n by n, that is plus 1. Okay? Can anyone, now what I'm going to do, the points on this left part of the region, I will write as x values. That is, this is x0, x1, x2 to xn. Okay? So this is my x0, x1, x2, this is my xn. And we, from this point itself, we were starting the second half of the partition. This I am going to write as y0. Is it okay? y0, y1, y2 to yn say. Are you getting me? Points on the left part of the region, we were writing, these points we are writing x0, x1, x2 to xn. From this point only we will start y0, y1, y2 to yn. Different symbols just we were using in order to write the partition. Is that okay? Is the partition understood?
No.
Now can you tell me the value of xi, ith in point of this first half, and yi, ith point of the second half? Then what is delta xi and what is delta yi? What will be xi?
Minus 1 plus 1 by n.
1.
Minus 1 plus I by n.
I by n.
And what is yi?
I by n. I by n.
Yes, it is I by n. And what about the length of every subinterval in both the half? Both the sections?
1 by n.
Yes, it is 1 by n. Okay? Okay? Now for the different parts of the region, to write the Riemann sum, we were selecting 2 points. Therefore, here Ti is a point in ith subinterval of first half, xi minus 1 to xi later. And the second we will select Ti dash, and which will belongs to the ith subinterval of second half, yi minus 1 to yi. And we were taking Ti as xi sec and Ti dash as yi. Okay, and this is for all I equals to 1 to n. Okay, means which interval, which points Ti I have selected? In the first interval, this is my T1, this is T2. Second endpoint of every subinterval we have selected, right? Up to this, any difficulty? If you have, you can ask me. Otherwise, we will write directly the sum, Riemann sum. Any difficulty in the partition?
No, no.
Yes or no? No. Okay. Now shall I consider the sum directly? Riemann sum we will consider, and we will check its limit. If limit is existing, the function is integrable. If not, it is not integrable. So let me write SP up. Now as we have made 2 different partitions, I will write the summation accordingly. Summation I equals to 1 to n f of Ti. For the first half, I will write delta xi. Then summation I equals to 1 to n f of instead of is Ti dash into delta yi. That is 2 different sums we have written for 2 different parts of the given interval. Is it okay? What is Ti dash we have selected? Yi. Ti is xi. Let me put both the values. This is f of xi delta xi plus summation I equals to 1 to n. This is f of yi into delta yi. Okay, make sure that this is the negative part and this is the positive part of your partition right now. Then accordingly tell me the function values. What will be f of xi for negative part? Yes, it is minus xi into delta xi. And what will be f of yi? Or false?
yi.
It is yi itself. Therefore, yi into delta yi. Now we know the values of xi and yi. Let me just put the values. What is xi we have selected? Minus 1 plus I by n. Delta xi is 1 by n. Added with summation I equals to 1 to n. Yi is I by n. Delta xi is 1 by n. Okay, let me absorb the negative here and let me just separate also. Let me absorb first. Plus this summation as it is, no? Okay, now let us divide the sum or let us just divide it here over this bracket. Therefore, what is my first sum? Summation I equals to 1 by n. Yes, 1. 1 by n, shall I write? 1 by n multiplying by 1 by n to the bracket. Summation I equals to 1 to n. This is I by n into 1 by n added with the same. Is it okay? Now look at the second and third term of the expression. Both are same, no?
Yes, ma'am.
Therefore, cancelling each other, we will have this first sum only. 1 by n is independent of I, therefore let me take it out. E remains with summation I equals to 1 to n, 1. This is your SPF value. Okay, what is summation 1 then?
N.
N. Therefore, may I say it is 1. Therefore, SPF itself is 1. Therefore, what about a limiting value? There is no n on the right side. Therefore, taking limit, there is no effect, no? Therefore, may I write limit n tends to infinity, SPF is equals to limit n tends to infinity 1, which is 1 again. What we have proved, limit of this given function exists. Therefore, the function is integrable. What is the integral value? What is the integrable value?
1.
Therefore, may I write minus 1 to n mod x dx is equal to 1. Okay, I will give a homework. Whatever the sketch we have drawn here, no, there are two triangles constructed actually. Okay, find out the area. Find out this area by calculating both the areas of the triangle and check whether it is giving you the value 1. Correct, na? Any difficulty in the example? If you have, you can ask me. The only part we have changed is as the function behavior is different on the different part of the given interval, we have changed, that is we have divided the interval into 2 parts and we have made the corresponding calculations. Yes? Any difficulty with this?
No, ma'am.
If not, let me go for some applications of this Riemann sum. Okay. Actually, we have proved the result that integration of an addition of two functions is addition of the respective integrations. Same result we will prove by using Riemann sum method. Previously, we have proved it by the first definition, no, Darboux theorem and all. Okay. So let me write some applications. Under this, we were going to verify the first theorem, which states that if f1, f2 and f equals to f1 plus minus f2 are bounded and integrable, then prove bounded and integrable on closed interval AB, then prove that integration a to b f dx is equal to integration a to b f1 dx added with integration a to b f. Okay, the same we have proved earlier, but now we are going to prove it by Riemann sum definition. It is given that all the functions are integrable f1, f2 and f1 plus minus f2. First we will prove the case of addition, then we will go for difference, right? Now time being, let me write the three definitions of function f1, f2 and f are integrable by using second definition, right? Riemann sum definition. For this, let me start with an epsilon positive. Let epsilon be any positive number. I will write since f1, f2 are integrable. Since f1, f2 are integrable, therefore, there exists delta greater than 0 such that, okay, first definition I am writing but in epsilon delta notation, such that for every partition p equal to, what is a partition we are writing in general, x0, x1 to xn with norm mu p less than delta, and for every choice of points in ith subinterval, comma, we have what we have. Yes, function f1 is integrable. Epsilon delta notation I am writing. What is another, limit definition? Limit mu p tends to 0. Yes, p f1 equals to integration a to b f1 dx. But in this discussion, we were writing the epsilon delta form of this definition. What is epsilon delta form? Mod of SPF1 minus integration a to b f1 dx is less than by epsilon. Correct now? Where norm p is less than delta. Already we have written, no? Partition we have selected with norm p less than delta. That is, what is the sum actually? Summation I equals to 1 to n. Is it f1 pi into delta xi minus integration a to b f1 dx strictly less than by epsilon? Let me call it as statement number 1. Okay. Similarly, let us write for the second function. SPF2 minus integration a to b f2 dx less than epsilon. Okay, that is summation I equals to 1 to n f2 ti delta xi minus integration a to b f2 dx less than by epsilon, and let me write as statement number 2. Now, if I wanted to construct f1 plus f2, okay, what will be the corresponding sum? SPF. What will be the corresponding SPF? Is it f1 plus f2 operated on ti into delta xi? Correct ना? SPF काय येईल आपला? F is f1 plus f2. Okay, let me write it afterwards. Now, first job I will do is adding these two equations. Inequality, sorry. What we get if I am adding these two? Adding these two, I wanted to convert it to less than epsilon. For that, I'll just adjust the epsilon value to epsilon by 2. Let me just add it. ऐकताय ना सगळं माझं? Yes,
Yes, ma'am.
Yes, ma'am.
Okay, this is less than by epsilon combined. Can I combine this modulus? अशी सिच्युएशन आहे बघा, मॉड एक्स लेस दॅन इप्सिलॉन बाय 2, मॉड वाय लेस दॅन इप्सिलॉन बाय 2 आहे. आपण ऍडिशन केली मॉड ऑफ एक्स प्लस मॉड ऑफ वाय लेस दॅन इप्सिलॉन केलं, तर तिथे ऍडिशन मॉडलेस कंबाईन करू शकतो का आपण? हे काय लेस दॅन बाय मॉड एक्स प्लस मॉड वाय लेस दॅन बाय इप्सिलॉन. मग मी असं म्हणेन का मॉड ऑफ एक्स प्लस वाय इज ऑल्सो लेस दॅन इप्सिलॉन. Can we combine this addition like this?
Yes, ma'am.
Yes, ma'am.
Hello? I think there was some network error. Therefore, it was not audible, I think. Right now?
Yes, ma'am.
Yes, ma'am.
We just share the screen again. Check. Up to which point you heard? 3, 4. I think first theorem was over, na? I have just explained again. बरोबर आहे का? संपला होता का theorem?
No, ma'am. Equation 2.
Equation 3 पर्यंत आलो होतो का आपण?
2, ma'am.
Equation 2.
हा?
Equation 2.
Equation 1 and 2 are actually the definitions we have written simply. Integrable means this statement number 1 we have. S2 integrable means mod of SPF2 minus integration is less than epsilon by 2. We have written and simply by adding 1 and 2. This I think someone told me yes, no? Mod x plus y less than epsilon. But we can combine the modulus here. Therefore, we have this statement number 3 with us. This is the limit. This is whatever the bracket I have drawn, no? This is the limit of your this sum, na? Riemann sum. Okay. Then knowing a function f equal to f1 plus f2 is integrable, this sum we have evaluated. What is the value of the sum? f1 ti plus f2 ti into delta xi. Let us use again the definition of integrability, which tells us that this is the limit of your Riemann sum. Okay. Therefore, looking at this number 3 and number 4, both are the limits of same sum. Can we have different limits for the same sum? If I am saying limit exists, if we were saying limit exists means it is unique as well, no? Right now, we cannot have two different limits. If we have two different limits, limit do not exist. Okay. So here, whatever the bracket we have drawn in this 3 is equal to this bracket in 4. So we have equated the values. Hence it is the proof, and then we can do the similar part for the subtraction as well. Okay. In the next lecture, we will go for some corollary. Here I will stop. Any difficulty if you have, you can ask. In the next lecture, we will go for one more theorem that we have proved already. Integration a to b is integration a to c plus c to b. By using the Darboux sum we have proved. Now we will prove by Riemann sum with few important theorems as well. Let us stop for today.